Hello, welcome and thank you for joining me for the first video on forces and friction for the Year 13 Mechanics bit of the A-Level Maths course. So this session we're going to actually revisit the old sine and cosine rule from Year 12 and GCSE, and we're going to also revisit something I very briefly mentioned in the moment section, which was resolving forces to our advantage so we can solve harder mechanics questions where we've got multiple forces acting at a point or an object. So to get us suitably warmed up, I've got a warm-up, as it's called, just 4 questions for you to attempt. Here they are. So might be an idea to pause the video now, try these on a sheet of paper or your handout if you've got it, and when you're ready to see what the answers look like, and if you've got them correct, press play, and I'll do my best to guide you through them. Rightio, well, let's have a look now at warm-up question 1. So here we're given 2 points A and B, where A is 1, 2 and B is 3, minus 1. Part A, hopefully fairly straightforward this. Write down the vectors OA and OB in the form xi plus yj, where I and j are the unit vectors in the x direction and y direction respectively. Well here, OA is just going to be how far we go along in the x direction, so because we're going 1 along for x, that's just 1i. And 2 means 2 up, so that's going to be just 2j. Whereas OB, because these coordinates are 3, minus 1, that's going to be 3i, and because it's minus 1 in the y direction, that's down 1 unit in the j direction, so it's minus j. Part B, hence find the coordinates of point C, where OC is just OA plus OB. So adding vectors, as you probably remember, well hopefully, is fairly straightforward. So OA is I plus 2j, and we worked out that OB was simply 3i minus j. So when we add these together, it's very much just like simplifying straightforward algebra. So group together the terms, and we're done. So OA is I plus 2j, and OB is this one. So group together the I terms. The total of the I components is 1i plus 3i, which is also just 4i. And 2j minus 1j leaves us with positive 1j overall. And so that's all we need to do for question 1. So let's have a look now at question 2. So question 2, we're using the answers to question 1 to draw on the vectors OA, OB and OC on this grid below. And so from O to A, we worked out that OA was just 1 along and 2 up. So if I add in OA here, let's just colour in OA in a red colour, just so it's clear which ones I'm talking about. So OA, starting from the origin, 1 along, 2 up, like so. That was because point A was 1 and 2, so this here is vector from O to A. In the same way, we can do OB. So from before we had that OB was 3i minus j. So the vector line representing OB will be a straight line starting from the origin, which goes 3 along and 1 down. So 3 along and 1 down. That represents the the position vector OB, because B is here, like so, and this is from O to B. Finally, OC, the position vector of C, we had was the summation of OA and OB, so that was 4i plus 1j. So that's 4 along and 1 up. And so OC could be represented like so. So 4 along and 1 up gets us to point C. And this vector here is OC. We're going to use this now for warm-up question 3. So for 1.3, we're asked to calculate the magnitude of OC and the angle that OC makes with the positive x-axis. So we're wanting essentially the magnitude and direction of OC. So reminding ourselves of the diagram from before, here's what we have. So OC, we simply just use some simple Pythagoras. So the magnitude of OC, essentially the length of this line as we go from 4 to 1. So we can just annotate on, in a different colour perhaps, this line here. So it goes 4 along and 1 up. So if we just draw this in, so 4 along and 1 up, and it's simply just for the length of this hypotenuse. So it's going to be the square root of 4 squared plus 1 squared, which, if you want to check on your class quiz, you can. This gives us root 17. And for B, finding the angle that OC makes with the positive x-axis, essentially we want to find this angle here. We know the opposite side is 1, the adjacent side is 4. We know the O and A, it's OA, as in TOA, so we use tan. And so for B, the angle it makes, which is theta, we're going to do tan minus 1, opposite, divide by adjacent, 1 divided by 4. So let's see what we get here. So shift tan minus 1 of a quarter. That gives us to 3 different figures, 14.0 degrees. And last for the warm-up, we have a standardish mechanics question similar to what you might find in year 12. So I have a box of mass 2 kilograms, it's been accelerated horizontally. So this is a warm-up, so we can assume here it's going to be a horizontal plane. And I'm going to draw on the box here. We're told it's 2 kilograms. If it's 2 kilograms, that means its weight is going to be 2g. It's been accelerated horizontally by a force of 15 newtons. So presumably there's a force here acting horizontally of magnitude 15. There's also a constant resistive force of 8 newtons acting opposite to the direction of motion. So possibly it's a frictional force, who knows? There's a force opposing the 15 of size 8. Calculate the acceleration of the box. I suppose for completion, we could maybe label on here there will be a normal reaction force. For normal reaction force, because the only forces acting here are horizontally, apart from the weight, the normal reaction force should counterbalance weight perfectly, so the normal reaction will be 2g to counteract its weight, so it's not going to accelerate through the floor or float up, which would be pretty weird indeed. So I calculate the acceleration. This is a simple application of F equals ma. So the resultant force horizontally is 15 minus 8, which is 7 newtons. So overall, there's a force 7 newtons in the positive x direction. There's a force of 7 newtons acting to the right as we look at this diagram. So the resultant force is 7 newtons. We also know the mass of this object, it's 2 kilograms. Therefore, we can apply F equals ma, rearrange this to find the acceleration a. So, therefore, we can say 7 equals 2a. So a is 7 divided by 2, which gives us 3.5 meters per second squared. Let's now have an explore about what this subchapter holds and the chapter in general. So let's start the main bit of the lesson. So, resolving forces in the direction of motion. Resolving forces is fundamental to mechanics. There's no getting away from it. You need to know how to do it to do well. The intuition behind resolving forces and the method are going to be described now. So the force F newtons is acting on a book placed on a table from the point A. What book, I hear you say? Well, here it is. There's your book. And the book moves horizontally, imagine, in the direction of B. So the book's sliding along the table to the right. The angle between the force and the direction of motion is theta. The force F can be represented as a sum of a horizontal and vertical component in the direction of x and y, respectively. It's my belief that resolving forces is found to be a fairly tricky concept because you're almost inventing two extra forces. You need to think of it as a decomposition of this diagonal force. You can think of a diagonal as so much across and then so much up or down. So it's imagining it split into literally its components before it was summed up to overall have this diagonal effect. So how do we do this? Well, this is the general method. First off, draw the force as a vector with magnitude f. Simple enough, so you draw something like this. Second up, draw the x and y axes with the origin as the starting point of a vector f, like so. Next, what you need to do is label the angle. Typically, this is the angle in between the x-axis and the direction of this f force. So we're going to put in a theta symbol here. Next, we need to label the x component as f cos theta and the y component as f sin theta, like so. And nearly there now. In fact, we have pretty much done. However, what you need to remember is both components, f cos theta and f sin theta, although it looks like f sin theta is floating here, you need to remember these forces originate from where the overall resultant force acts as well. So a more useful representation of this will be to slide this f sin theta back to the origin, the true origin of this force, so you have this effect here. Generally speaking, if f is the hypotenuse, then you've got an angle theta to the horizontal or sometimes a vertical. The force usually going along is f cos theta. The easier way to remember it is the force which goes up or down is always the hypotenuse, which is f multiplied by sine of the angle. So the component opposite to the angle is always hypotenuse sine of the angle. The other one is f cos angle. So I'd always do the opposite component first, which is always the hypotenuse multiplied by sine of this angle, in this case f sine theta. Let's do some worked examples using this idea. So number one, we have a force of magnitude 5 newtons and it makes an angle of 30 degrees anti-clockwise with the positive x direction. We need to write f in the form pi plus qj, where p and q are constants to be found, and I and j are unit vectors in the x and y directions, respectively. So, first of all, let's just sketch this out. So, we're told this makes an angle of 30 degrees clockwise from the positive x direction. So, labelling this on. So, if that's x, 30 degrees clockwise, anti-clockwise I mean to say, means 30 degrees up, like so. Essentially it means 30 degrees above the x-axis. We're told as well this has magnitude of 5, so I'm going to label this on here. And this angle is 30 degrees. Remembering we were told it was anti-clockwise, so this angle here is 30 degrees. So we need to resolve this into two separate components. So like I said earlier, I do think the easiest thing to do first is to do the opposite side. So if I just split this into a nice dotted line, as it were, then this the vertical component opposite to the angle is going to be the hypotenuse 5 sine of this angle. Whereas the component going along in the direction of the x-axis, this is going to be 5 cos 30. But because we need to give this force in the form pi plus qj, we need to actually evaluate what 5 cos 30 and 5 sin 30 are. So let's do 5 sin 30 first. So 5 sin 30 is 5 over 2, that's easy, that's 2.5. Whereas 5 cos 30, so 5 cos 30 gives us 2 3 sig figs, 4.33. I suppose we could label these in newtons because they are. So therefore, in pi plus qj form, in unit vector form, F is 2.5i. Sorry, talking absolute garbage. Going along is the I component, so this is 4.33i. My sincere apologies. Plus 2.5j, which is acting in the positive j direction. Let's try another one. So question 2, we have a magnitude of 4 newtons this time of the force, and this time it's making an angle of 110 degrees anti-clockwise with a positive x direction. So again, let's just label this on here. So that's the x direction, and then this is 110 degrees from there. So drawing this on, 90 degrees would be perpendicular, 110 degrees is a bit more of a turn, something like this. So I'm going to label this angle here 110 degrees. But of course, it might be easier to think of this in terms of an acute angle. So if I label the y direction going up like so, then obviously that's 90, so the extra bit is going to be 20 degrees. So what we need to do after drawing the diagram, which we have done, apart from labelling on the magnitude of the force, which is 4 newtons, we need to write F in the form AI plus BJ, where A and B are constants to be found. So what I want to do here is just to zoom in on this bit of the diagram before we do part B. So that's part A done. Part B, otherwise the diagram's going to get a bit slightly too crowded. So this is 20 degrees. That was 4. So we can now split this into components. So like I say, probably do the opposite component first, which is always going to be the hypotenuse sine of this angle we know. So in the I direction, we're going to have 20 sine, sorry, 4 sine 20. And going upwards is going to be 4 cos 20. So along is cos, opposite sine. And of course we need to actually work out what these values are. So 4 sine 20, let's do that one first. So 4 sine 20 gives us approximately 1.37 to 3 significant figures. Whereas 4 cos 20 gives approximately 3.76. So for part B, I can say F is therefore this is the component going along, so this is the component relative to I, but because this is going to the left, this is going to be a negative. I is measured to the right, so because this 4 sine 20 is going this way, it's going to the left, that's a minus 1.37. So it's going to be minus 1.37 I, but because the vector is going up, which is in the same direction as the positive j direction, this is going to be positive, so plus 3.76 j. So one more before I reintroduce the cosine rule and the sine rule as well, I suppose. This time we've got another box on a floor. So a box of 3 kilograms lies on a smooth horizontal floor. A force of magnitude 6 newtons is applied to the box at an angle of 60 degrees to the horizontal, causing the box to accelerate. Find the acceleration and find the normal reaction. So draw a carefully labelled, nice, big, clear diagram. The first thing I'd say to notice is we're told it's a smooth horizontal floor. This implies no friction. So there's going to be no resistive force due to friction unless one's mentioned in the question, which in this case it's not. So you can draw in the box. It's 3 kilograms, so therefore the force due to its weight is going to be 3g. Normal reaction acts always perpendicular to the surface. So for normal reaction, I'm going to label N, like so. No friction, so there's no force opposing the motion, but there is a force of magnitude 6 newtons, and it's applied at an angle of 60 degrees to the horizontal. So this force here is going to be a force which is going upwards at about a 60, well exactly I should say, a 60 degree angle. So it's got a magnitude of 6 newtons, and that's 60 degrees. Why is it 60 degrees? Because it says it's 60 degrees. So label this on like so. The colouring, I will admit, is completely unnecessary, I just like doing it, so forgive me. So what we now need to do is to calculate the acceleration of this box. On second thoughts, this 6 newton might be a bit hard to read, so I'm just going to label that as 6 newtons as so it's a bit clearer. That's going up. So for part A, the acceleration of the box. So the acceleration is basically going to go horizontally. There's going to be no acceleration going upwards. There's no mention of this box being lifted up or pulled downwards. So what we can do is resolve horizontally. So the force is 6 newtons, so what we could do here is resolve horizontally and I suppose actually also vertically. Let's just do both. So the vertical one, like I said before, it's always going to be the magnitude of a force, the hypotenuse in this case, and sine of the angle in question. So this component of the 6 Newton force is 6 sine 60, whereas the component along this floor, or the table, whatever it might be, whoops daisy, is going to be 6 cos 60. So, because the acceleration is only going to be in the horizontal direction, we can apply F equals ma. The only force going horizontally is going to be the 6 cos 60. Because there's no force opposing it horizontally. And that's going to equal the mass of the object, which we know is 3 kilograms, multiplied by the acceleration. So 6 cos 60 equals 3a. Therefore, if we divide both sides of this equation by 3, we see that the acceleration will be 2 cos 60, which we can easily work out because we've got one of these devices, often known as a calculator. So 2 cos 60, which have it, gives us 1. If you don't remember, cos 60 is one of these exact trig ratios, which is 1/2, 0.5. So that's going to be exactly 1 meter per second squared in the positive x direction. For B, we need to find the normal reaction. So, resolving vertically, because the object isn't moving up or down, it's just going along here, this box, we can say that the total of forces going up will equal the total of the forces acting down. So forces acting up, we've got N, the normal reaction force we're trying to find, and also we've got 6 sine 60. The total of the forces going downwards, well, that's just for weight, which is 3g. So therefore, just rearranging this, N is going to be 3g minus 6 sine 60. Hopefully remember what g is. G is 9.8. If you're studying physics, physicists like to give us to 9.81. But anyway, in this course we're going to take g to be 9.8. So 3 multiplied by 9.8, subtract 6 sine 60, and that's going to give us, to 3 significant figures, 24.2 newtons. And that's worked example 3 completed. There is an alternative to resolving forces to solve problems, although like I said before, resolving forces really is a bread and butter method. In my humble opinion, you need to know. If you're going to really stamp your feet though and want an alternative just in case, I'm going to give it to you here, and it uses the cosine rule and sine rule, so take my word for whatever you want. For this, in my opinion, I'm going to give you a massive, massive warning sign. Use this next method with caution. It can get quite ugly, and in my opinion, you're going out of your way if you use this rather than simply resolving forces. Anyway, let's have a look at this alternative now that I've bigged it up so much. It's called the triangle law. So you can use this triangle law of vector addition to find resultant forces without resolving them into components. So let's just take a fairly simple example. So let's consider the position vectors u and v as shown in this diagram relative to some fixed origin O. So here, as you can see, u makes an angle with the positive x direction of 30 degrees anti-clockwise, or 30 degrees going upwards, whereas v is making an angle of 45 degrees clockwise with the x-axis, or 45 degrees downwards, you could think of it as. You should hopefully remember from year 12 that vectors can be added, putting the tail next to the head of another one. So imagine sliding this v and putting it at the end of u, so we have u and then v, like so. I'll explain these annotations in a moment. So the vector v can be translated so that v is no longer a position vector, and the origin of v, as it were, becomes the endpoint of u. Like I said, vectors can be joined by putting the beginning of one at the end arrow of the other. Notice as well always that the magnitude and direction of V are preserved by translating it from one point to another. Its direction won't change and its magnitude won't change. We can then work out some extra angles. So if we look here, for example, we knew that U acted 30 degrees going upwards, and so if I add in 30 degrees there, like so, like it was, we can return to GCSE for a second and remember alternate angles. So alternate angles are equal, that's why this one's 30. In a similar way, if I were to just draw it in the line at the bottom here where this R is, I'll mention this R in a moment, that's a bit of a thicker line, so I'll just alter this, if you bear with me for a moment. Likewise, we had that V was going 45 degrees down, so likewise if you wanted, we could say that's 45 degrees going down like so. Angles on a straight line, of course, add to 180, and so if that's 45 degrees and that's 30, that adds to 75, that gives us 105. So then we might be able to use the cosine rule, for example. If we knew the magnitude of U and V and the angle in between, we could work out this vector here, R. So what is R? Hopefully you know, but just in case, the resultant vector is R. The resultant vector R is essentially the third side of this triangle formed by U and V added together. And that's essentially the triangle law. So we can manipulate vectors by translating one to another position, and then the resultant of one added to the other makes the third side. In this case, the resultant force, if U and V are two separate forces acting on a body. Let's just have a look at an example how this might be used. So we've got two forces, F1 and F2, acting on a particle. F1's got a magnitude of 8 newtons, makes an angle of 30 degrees above the positive x direction, whereas F2 has magnitude 5 newtons and is making an angle of 45 degrees below the positive x direction. Calculate the magnitude and direction of this resultant force. Method 1, this is by far and away my preferred method and the method I'm strongly recommending to you folks. So what I'm going to do here is just add on the positive x-axis like so. Then we can label on the extra information. So we've got here F1, magnitude 8, and it's 30 degrees above the positive x direction. So let's call this F1. So F1 is 8 newtons magnitude, and it's acting an angle of 30 degrees above the positive x-axis like so. Whereas we've got F2 as well, so I'm going to draw this one in. F2 only has a magnitude of 5. It's making an angle of 45 degrees below the positive x direction. And so this one's going to be acting sort of down here like so. It's going to be 5 newtons in size, in magnitude. And this one is acting an angle of 45 degrees below the positive x direction. So what we could do here is just simply resolve these components. So if we think about resolving opposite to these angles, remember opposite is always going to be sine. That is not a straight line like I wanted. There we go. I'll put these into red. So the 8 Newton force, this component here acting perpendicular to the x direction will be hypotenuse sine angle, like I mentioned before. So this one here is going to be 8 sine 30, whereas this one here going downwards is going to be again hypotenuse sine angle, in this case 5 sine 45. They'll also have horizontal components, both of these forces of 8 newtons and 5 newtons. So if I label these on as well, for 30 Newton force, I'll go that way, and the horizontal component of the 5 Newton force will again go this way too. Now they're originating from what might well be the same point particle, but I'm doing these lines slightly apart so you don't confuse one with the other. But essentially, if this is a particle they're both acting on, then these two will originate from the same point. So forgive this slight inaccuracy, it's just for illustration and making the point clearer. So if this one here going opposite is sine, the one going along this direction, normally the direction of the force, is cos. So for the 8 Newton force, the horizontal component will be 8 cos angle, 8 cos 30, whereas for the 45 degree angle and the 5 Newton force, this one going along is going to be 5 cos 45. So we can now use this information to build a picture of what's going on. So we can sum the horizontal components and we can sum the vertical components too. So if we take this direction as the positive, we can say the sum of the forces acting horizontally is going to be 8 cos 30 and 5 cos 45. Because they're both acting in the same direction, they're both going to be positive. So 8 cos 30 plus 5 cos 45. Let's work out what this is. So 8 cos 30 plus 5 cos 35. Make sure to close the brackets off as well when you're typing in it on your calculator, otherwise that will really mess up the syntax. So press equals. We get this horrible looking surd. We could, if we want to, get it into decimal form like so. This isn't our final answer, so don't round it too much. Normally answers, when we finally give the answer, are given to 3 significant figures, so if we are going to round it, give it to much more than 3 significant figures. Let's call it 10.463737. 10.463737 newtons. That's the total of the force which is going in a horizontal direction. We can now also work out the total force going either up or down. So if I just take, for example, up as the positive direction when I'm resolving upwards, then the total force going up is going to be 8 sine 30, because that's going in the same direction, minus 5 sine 40, because 5 sine 45 is going in the direction opposite to what I'm deeming as being positive. So then minus 5 sine 45, and that gives us a total force going either up or down. Let's work out which prevails, if it's going to be positive or negative. So 8 sine 30 subtract 5 sine 45. Horrible surd again. Press the sad button. So it's just slightly positive. So it's 0.464466. So 0. Oops, I'll get a different colour actually. 0.464466 newtons. We can now build a picture of this resultant force. So if I just take this one here and that one, carefully does it, we can now build a picture of what the resultant force of the 8 and 5 looks like. So it's going to go about 10.5 newtons along and ever so slightly up. So it's going to be looking something like this. So again, we've got 10.466, whatever, this horrible decimal going along, and slightly up 0.46-ish going up. So we want the magnitude and direction of this resultant force, so we can now begin to think about this. So I'm going to call this resultant force, rather unimaginatively, I'm going to call it R. And we've got it as 10.463737 going along in the positive x direction, and we calculated it was 0.464466 newtons going upwards. Therefore, the magnitude of this resultant force is just, again, Pythagoras, albeit with fairly awkward numbers. So it's going to be 10.46 whatever squared plus 0.46 whatever squared. So if you calculate this, so square root of 10.463737 plus 0.464466. Make sure we square both of these as well. We're getting 10.474. 10.474, so round that to three significant figures again, 10.5 newtons. So 10.5 newtons to 3 SF. And the angle it's making here with the horizontal, if we call that theta. I know the opposite, I know the adjacent. So I can do tan minus 1 to work out this angle theta that the resultant is making with a positive x-axis. So theta is tan to the power minus 1, 0.46, so on, divided by 10.46, so on and so on. Let's see what that gives us. So shift tan minus 1, 0.464466, and divide that by 10.463737. I get to three significant figures 2.54 degrees. So magnitude, 10.5 newtons force, and the direction of the resultant force is 2.54 degrees. Now, we can work out this using the cosine rule, and like I say, you might have thought this looks fairly ugly anyway, but the cosine rule isn't much better, if at all. So, again, what we could do is draw on these forces. So we've got the 8 Newton force, which is going upwards at a 30-degree angle, and then we can have this 5 Newton force joining to the end of this one like so. Then the resultant force will be the third side of this triangle like so. So what we can do here is think about what we need to work out. So the direction of resultant force is this angle here, which obviously we can calculate soon enough. And the size of the resultant is just going to be the length of this red line, whatever that might be. So let's label on the magnitudes. So 8 newtons that way, 5 newtons going down, and of course we knew this was a 30-degree angle going up from the horizontal, because it acts 30 degrees up from horizontal. This here is, I've labelled here the x-axis, so all of this angle there is 30 degrees. So the 30 degrees includes that slice of purple, whatever that might be, pretending we didn't do this method here. And this 5 Newton force is going downwards at 45 degrees. So again, if I just label this on like so, then we knew this was 45 degrees. Using the idea of Z angles, alternate angles, if this angle here is 30 made with the horizontal, then this one here would be 30 degrees as well. What we could then do, similar to the generic example I gave introducing this cosine rule, angles on a straight line add up to be 180 degrees. So if this is 30 and that's 45, which sums to 75, this angle here in the middle will be 180 minus these other two, 180 minus 75, which gives us 105. So we know this angle here, and we know the magnitudes of the two sides of this triangle, either side of the angle we know. So if I call this one R, then I can use a cosine rule here to work out the magnitude of R. The cosine rule, if you recall, is a squared equals b squared plus c squared minus 2bc cos A. So that is essentially the cosine rule. So if we apply this here, where A, B, C are the sides, we want to work out side A, which is opposite to the angle we know, angle big A. So in this case here, side A is R, B and C in any order at the 8 and 5, angle A is 105. So therefore, the magnitude of this resultant force, magnitude of R, is going to be the square root of 8 squared plus 5 squared minus 2 lots of 8 multiplied by 5 multiplied by cos of this 105. And that's going to give us, well, let's see what it gives. So square root 8 squared plus 5 squared minus 2 times 8 multiplied by 5 multiplied by cos 105 gives us, again, 10.47, and again that rounds to 10.5 newtons as we had from before, which shouldn't surprise us. It should be the same, but it's just nice to see that different methods do agree, just to validate what each method is in terms of being correct. So 10.5 newtons, again that's to 3 significant figures. However, using this method, this is when it gets a bit more complicated, yet still. We need to work out the direction of the resultant force relative to some given direction. So again, sticking with what we did before, let's give the direction relative to the horizontal. So this purple angle here, this tiny one, I'm calling theta. So theta is this tiny purple angle, like so. This 30-degree angle included theta here. And so in terms of this triangle from R up to 8 isn't the full 30. This triangle here is actually just going to be a tiny bit less. This angle in the triangle, just trying to find a nice colour I could use. Let's go for this one here. This is going to be 30 minus theta. which I'm going to label on now. That's 30 minus theta in this light blue colour. And the purple is theta. So that plus theta gives a full 30. So just thinking of this triangle here, the 8, 5R triangle, we can apply the sine rule to work out this theta. So, the sine of this tiny angle here, just this blue section, sine of 30 minus theta, divided by the side opposite to it, which is 5, that equals sine of 105 divided by r, which we just worked out. So therefore, whatever 30 minus theta is, multiplying both sides by 5, then doing sine minus 1, that's going to be sine minus 1 of 5 sine 105 divided by r, which we've worked out from before, so we can use this again. So this is r stored in the calculator, so I'm going to use this exact value. So if I press A and S, look, it's stored nicely for us. So shift sine minus 1, 5 sine 105, close brackets important, divided by that answer, which is the magnitude of r, close the big brackets, we get 27.458. So in other words, 30 minus theta is this. So again, we need to rearrange, we're still not finished. So 30 take away what gives 27.458. We rearrange this, we can add theta to both sides, then subtract 27.458 from both sides. So theta is 30 minus 27.458, etc., etc. So let's do this now. So we've got the 27.458, whatever. So 30 minus that, 30 minus A and S, gives us 2.54 degrees. To three significant figures. And again, you can see from before, that does agree, because we had 2.54 degrees from before. So if you're thinking the cosine rule looks confusing, you're not alone. I'm with you on that too. Don't really have to use it. With practice, you can get good at it. But my preference and my focus in this chapter will be resolving forces. So apart from this next example, you might not see the cosine rule too much again in this chapter. I'm going to give one final worked example now before you get set off trying these on your own. So this time just resolving components, this time with 3 different forces to consider. So 3 forces act upon a particle as shown here. Given that the particle is in equilibrium, so it's not accelerating in any direction, calculate the magnitude of P. So my suggestion here is, as ever, just to resolve these forces. So first off, I'm just going to colour code these different lines. So if I go for 140 newtons in green, then going this way, going to the left, we're going to have a force of 140 cos 45 when we resolve. And opposite, like I said before, is always magnitude sine of the angle. So going up is 140 sine 45. If I now think of this 100 Newton force, do that in a different colour, let's say, do this one in blue, then for this one, going upwards, upwards or opposite, in this case is always magnitude sine angle, so that's going to be 100 sine 30 upwards. Going along is magnitude cos angle, so in this case 100 cos 30. Finally, P is the one we want to really work out, magnitude of P. It's acting at an angle of theta, so that means the opposite component will be P sine angle, so just P sine theta, whereas going along, bit of a crowded diagram here again, that's going to be P cos theta going along. We now need to use this fact that the particle is in equilibrium. So in equilibrium, so therefore the sum of the forces going up or down is 0, and the sum of the forces going left and right, or horizontally, is equal to 0. So if we just take, we can take them in any order to be fair. I'm going to go vertically first, can't even talk, vertically first, get my teeth in. So taking vertical components, it's all going wrong. So vertical components of these forces. Essentially, the sum of the forces going up and down will be equal to 0. So forces going up will equal forces going down, to put it simply. So going up, we've got 140 sine 45. We've also got 100 sine 30. The only component going down is just P sine theta. So therefore, we can simplify this and just say P sine theta is whatever this thing here is. So 140 sine 45 plus 100 sine 30. So goodness knows, let's work it out. So 140 sine 45 plus 100 sine 30. Press equals. Because it's not a final answer, you could either leave it in this exact form, or if you are going to round it to lots of decimal places, because this isn't our final answer. I'm going to leave it like this. I'm going to leave it as 50 plus 70 root 2. So I'm going to just box this off for the meantime. Now I'm going to think about horizontal components. Basically forces going left and right. So going to the right, we've got two forces. We've got 100 cos 30 we've also got P cos theta acting to the right as well. So plus P cos theta that's going to equal the forces going to the left. The only component acting to the left is just this 140 cos 45. We've not mentioned this, but I'll just mention it now. Importantly, when you resolve forces into their components, you essentially forget about the individual forces altogether, because these individual forces have been replaced by their constituent parts. They've been replaced by their components. So we ignore this 140 on its own, this 100 on its own, and the P. For example, this 140 has been replaced with these two, making the 140 on its own redundant. We never use the components and the resultant. We use the resultant or the components. So, going back to here, we can rearrange this to get what P cos theta is in exact form. So P cos theta is going to be 140 cos 45 minus 100 cos 30. So let's just do this one. So what do we get if we do that? Whoops. get 140 cos 45, close brackets important, minus 100 cos 30. Let's see what that is. We get this awful looking thing here, minus 50 root 3. And what was it? I've forgotten. Plus 70 root 2. Box that one off as well. Now, this looks like we've hit a barrier. How would you proceed from here? I'm going to remind you of something from year 12. Just remember, tan is sine over cos. So it all links to everything else. So tan is sine over cos. So if I call this equation here Roman numeral 1, and this one Roman numeral 2, or II, then if I were to do 1 divided by 2, p sine theta divided by p cos theta on the left, the p's will cancel. I'll have sine theta divided by cos theta, which give me tan theta. So then I'll get tan theta equals 50 plus 70 root 2. All divided by this minus 50 root 3 plus 70 root 2. So what we can do is inverse tan this. So therefore theta will be tan minus 1 of that absolutely awful stuff. To be honest, I can't be bothered typing it all out, so this awful stuff would just mean all of this mess here. So let's work out what that is. So these questions can be ugly, like you're probably spotting here. So I've got this here, which is the denominator. I'm going to leave that as it is. So shift tan minus 1, 50 plus 70 root 2 on the top, divided by what I just had on the bottom, which is my previous answer. I'm going to just keep stored on my calculator. Close brackets, press equals. I get a very big angle indeed. So the size of this angle is pretty huge. It's almost perpendicularly down, but it's not quite. It's 85.245 and so on. 84.245 I'll call it. So now what I can do, I can substitute this value of theta back into one of these equations here. I can pick either 1 or 2, it really doesn't matter. So I'm going to sub this back into 1, just because 1 comes before 2. I'm that imaginative this late at night. So sub this into 1. So now I know what theta is. I know that theta is this awful looking number here. I can just take this here and divide it all by sine theta, what I've just worked out. So scroll down slightly. So P, or the magnitude of P, is going to be 50 plus 70 root 2 divided by sine of 85.245, whatever that comes out to be. Again, because this isn't the final answer, don't round this 85.245 too prematurely. Even though we have worked out what theta is, so we should be slightly proud of ourselves. So theta's in exact form on this calculator. I'm going to leave this as the stored answer. A and S equals theta, like you can see. So 50 plus 70 root 2, all divided by sine of that answer, which was theta, press equals. We get 149.5. 5 makes it round up, so to 3 sig figs it's 150 newtons. So the magnitude of this force P is approximately 150 newtons. So, like I said earlier, I will just briefly mention how you could have done this using the cosine rule. So, I've taken the liberty to pre-draw out the diagram by just shifting these vectors around into a force triangle. If you were to do the cosine rule, if you want to try it now before I reveal it, press pause and try and make the diagram now from which to apply the cosine rule. So press pause now if you want to. 5, 4, 3, 2, 1. Right, I'm going to reveal. You should have a diagram a bit like this. Okay, so this 100 vector here, I've done the colours differently, but never mind. P going down, I've done P in blue rather than red, but hopefully you see what I'm doing here. So, using this idea here, because P is going down by theta, like so, this 140 angle is going up at 45 degrees. I can use some Z angles here. If that's 45, this angle here will be 45. Likewise, this 100 Newton force here was going up 30 degrees, so I can call this 30 degrees here too. That means the total angle in this corner, if I just colour code this in a nice blue, this angle in the 100, 140 P triangle will be 30 plus 45. The total of this blue-ish angle I've coloured in is 75 degrees. So I can now use a cosine rule to calculate the magnitude of P. So magnitude of P is the square root of that side squared plus that side squared, 100 squared plus 140 squared, minus 2 lots of the product of those two sides, multiplied by cos of the angle opposite to P, which we can see as 75. In this particular case, it just so happens that the cosine rule works very nicely. It won't always, far from it. So again, if we calculate this here, square root of 100 squared plus 140 squared minus 2 times 100 times 140 times cos 75, close brackets. Again, you get exactly the same figure. So again, rounded to 3 sig figs, it's 150 newtons. And that's plenty for one day, I think. Over to you lot. My suggestion is to try all of exercise 5A, because it's quite a difficult thing to get your head around, and there's no getting away from it. You need to be good at either resolving forces or the cosine rule. My strong suggestion is get used to resolving these forces. Try the whole of exercise 5A, check your answers as you go through regularly. Don't make loads of mistakes and only realise at the end. Check regularly by using the solutions or asking me. Thank you for listening once again. Do consider subscribing, it's always nice and appreciated when you do. Take care of yourselves, and I hope to hear from you all soon. So, bye for now.